All right, so this is section 2.2, part 2 video. And in this part of the video, we're just going to talk about the standard normal distribution and how we can perform calculations based off of the standard normal distribution. So we talked about how a normal distribution was a distribution that was symmetric, unimodal or single-peaked, and bell-shaped. And so if we take the normal distribution and we standardize the values, meaning we change them into z-scores, what we end up with is what we call the standard normal distribution. It's a normal distribution with a mean of 0 and a standard deviation of 1. As we talked about, when we standardize all the scores in a distribution, the mean ends up at 0 and the standard deviation ends up at 1. So because all normal curves are exactly the same when we standardize them, we can pretty easily find the areas under any standard normal curve using the standard normal distribution. And so we'll talk about how to use tables as well as the calculator in order to calculate values for these normal distributions. So first and foremost, if I want to find the area in any normal distribution, there are a few things that I need to do. And I'm going to have you write this down here, and then we'll practice it in class as we go over questions, because it's very important that you include certain things in your responses to free response or short answer questions. And so in order to find the area in any normal distribution, the first thing you want to do is you want to make sure that you state the kind of distribution that you're looking at. In this case, a normal distribution, and that you state the values of interest. So the easiest thing to do would be to state that it is a normal distribution. So you can use the letter N to represent the fact that it's a normal distribution, and then in parentheses include your important values of the mean and the standard deviation. You could then also write out what exactly it is that you're looking for. So the probability that X is greater than, less than, whatever it is that you're looking for, a specific value, okay? Then you're going to draw your normal curve with the area of interest shaded and the mean and the standard deviation as well as boundary values clearly identified. So you would draw your curve, you'd put in your mean, you'd put in the values of standard deviations, right? And you put all of that in your curve. Then let's say you're looking for this specific area. You draw the boundary of the area and highlight shade, whatever it is that you're looking for. So once I've got that set up, the next thing I'm going to do is I'm going to perform my calculations, and I'm going to make sure that I show any of my work that I'm doing. So we're going to do one of the following. We're going to compute a z-score for each boundary value and use the standard normal table or technology to find the desired area under the curve, or we're going to use the normal CDF command and label each of our inputs, okay? And then we're going to make sure that we've answered the question. So go back and make sure that you have an appropriate answer for your question. Now, if we're working backwards and going from areas to values, we're still going to state our distribution. We're still going to draw the normal curve with the area of interest shaded, mean and standard deviation, and your unknown boundary value clearly identified. Then we're going to perform our calculations, showing our work by doing one of the following. We're going to either use the standard normal table or technology to find the value of z with the indicated area under the standard normal curve. Then we're going to undo that standardization. So we're going to transform back to the original distribution, or we're going to use the inverse norm command in our calculator, and then we're going to make sure that we've answered the question. So when I'm referring to the standard normal table, what I'm referring to is this table right here. And so you'll notice that the table is based off of a normal distribution, and that it tells us that the probability, so this shaded area right here, the probability of being less than whatever that specific z value is, right? So this is our specific z value. The probability of being less than is what we find in the table. So if you have a z-score, let's say we wanted to find the probability that z is less than negative 3.27. So I would go to negative 3.2 and then cut across to the 7 And this right here is the probability of being less than negative 3.27. Now, on the other hand, if I wanted to find a probability that z was greater than negative 3.12, I would need to take the total area of 1 and subtract negative 3.12, 0.009, and that would give me my probability for z being greater than negative 3.12. We'll look at these more in class. Obviously, there are calculator functions that can do this for us as well. And so we'll take a look at all of these different options and make sure that you feel comfortable answering these questions. Okay? Then the last thing in this section has to do with how we can assess normality of a distribution. So it's important for us to be able to determine if a distribution is normal and can be modeled by a normal curve in order to be able to answer some questions. So in order to do that, we always want to look at a graph of the data. So you could look at a histogram, you could look at a dot plot, a stem plot, and try to determine whether or not the graph was roughly symmetric, unimodal or single peaked, and bell-shaped. Another option is to create a specific display, which is called a normal probability plot. Now, a normal probability plot is a scatter plot of the ordered pair, your data value, and its expected z value. So a scatter plot is kind of like when you plot in algebra, when you have x, y coordinates. So the data value is going to serve like your x coordinate, and the expected z-score serves like your y coordinate. So you're going to have a bunch of points that are being graphed, because they're the points for each of the individuals in the quantitative set. So the x-coordinate, like I said, is the actual data value. The y-coordinate is the expected z-score that corresponds to that particular value, okay? Excuse me. If the points on a normal probability plot lie close to a straight line, then the data are approximately normally distributed. If there's a nonlinear form in the normal probability plot, then that would indicate a non-normal distribution. So if you were to look at the three graphs here, sample 1 is pretty linear. Oops. Okay. Sample 2's got a little bit of a jog there, but still pretty linear. Sample 3 also pretty linear. Now when we look at this last one, you'll notice a significant curve, and so that would show us that it's a non-normal distribution. And so depending on what the curve looks like, this one would look something like this, which leads me to believe that the set of data that it comes from is skewed to the right. Okay? So again, a normal probability plot gives us a way to assess normality where we can kind of look at something a little bit easier. We don't have to look for the shape of the actual set of data through the histogram or dot plot or stem plot. As I said, we'll go over all of this in class. We'll work on some examples, and hopefully you'll be clear on all of this by the time we're done in class. Thanks.